In this video, we will be discussing plate tectonics and rock deformation. Looking at a world map, you may have noticed that some continents have matching shapes, like pieces of a puzzle, particularly South America and Africa. Scientists have wondered about this fit of the continents since the first accurate world maps were produced hundreds of years ago. In 1912, German geophysicist Alfred Wegener proposed a hypothesis to explain the continental puzzle. He hypothesized that the continents had moved together by the end of the Paleozoic era, forming the supercontinent of Pangaea, which then started to break apart near the beginning of the Mesozoic era. The formation and breakup of supercontinent Pangaea were part of a repeated cycle in which pieces of the lithosphere moved together, split apart, and eventually reform again. Over the billions of years of Earth's history, this cycle may have repeated itself dozens of times. According to Wegener's hypothesis, the moving continents slowly plowed across the seafloor in the process of something he called continental drift. As proof that the now widely separated land masses had once been joined together, Wegener cited several types of evidence, including matching rock formations on opposite sides of the Atlantic Ocean, and matching fossils from Africa and South America. Wegener could not, however, provide a plausible mechanism to explain why continental drift occurred. Most scientists of Wegener's time rejected his hypothesis because it lacked a mechanism for driving continental movement. Today, we know that Wegener's hypothesis was correct. Continental pieces once did fit together, and they not only migrated to their present locations, but also continued moving and continue to move at an average rate of about 6 centimeters or 2.4 inches per year. Since the 1950s and 1960s, modern science built the theory of plate tectonics, the now universally accepted scientific theory that the lithosphere is divided into several moving plates that float on the asthenosphere. The continents move as part of pieces of lithosphere called lithospheric plates. These are also called tectonic plates. These enormous and unevenly shaped slabs of the outer crust and upper mantle are usually composed of both continental and oceanic lithosphere. Plates can vary greatly in size and thickness. Earth's present lithosphere is divided into at least 14 plates, of which about half are major and half are minor in terms of area. Plate tectonics involves several processes, including upwelling of magma, lithospheric plate movements, seafloor spreading, and subduction. The effects of plate motions include earthquakes, volcanic activity, and deformations of the lithosphere, such as warping, folding, and faulting that result in mountain building. This slide shows how the processes of plate tectonics form and cause changes in Earth's continental and oceanic lithosphere. The key to establishing the theory of continental drift was a better understanding of the seafloor crust. As scientists acquired information about the depth variations of the ocean floor, they discovered an interconnected worldwide mountain chain termed mid-ocean ridges. These submerged ridges occur at divergent plate boundaries, cracks in the lithosphere where plates move apart and pockets of magma form beneath the surface. Some magma rises and erupts through fractures and small volcanoes along the ridge, forming new seafloor. As the plates continue to move apart, more magma rises from below to fill the gaps. The upwelling of magma in the ocean floor creates new areas of ocean crust. This process, called seafloor spreading, is the mechanism that builds mid-ocean ridges and drives continental movement. Over millions of years, seafloor spreading has produced the oceanic lithosphere covering more than 70% of the Earth's surface. Geomagnetism is the study of phenomena associated with Earth's magnetic field. In igneous rocks, geomagnetism affects certain minerals, thus providing evidence for seafloor spreading. As lava erupts along a mid-ocean ridge, magnetic particles in the cooling lava align toward magnetic north. As the lava hardens, these particles lock in this alignment, creating an ongoing magnetic record in the lithosphere of Earth's polarity. Earth's magnetic field has a property called polarity, in which the magnetic poles have either positive or negative polarity. Over geologic time, the magnetic field's polarity reverses at irregular intervals. This chronology of reversals in Earth's magnetic field produces a clear record of ages for rocks on the ocean floor. Notice in the slide that the magnetic record pattern of stripes of rock is the same on both sides of the ridge. This symmetrical pattern reflects the fact that the corresponding stripes on each side of the ridge were formed at the same time. The youngest lithosphere anywhere on Earth is the new lava at the spreading centers of the mid-ocean ridges. Overall, the seafloor is relatively young. Nowhere is it more than 200 million years old, which is remarkable when you remember that the Earth's age is 4.6 billion years old. Subduction occurs where plates are colliding. The denser subducting slab of lithosphere exerts a gravitational pull on the rest of the plate. This pulling draws the plate into the trench. The subducted portion slides down into the asthenosphere, where it remelts and eventually recycles as magma, rising again toward the surface through deep fissures and cracks in crustal rock. This process effectively destroys older oceanic lithosphere. As subduction occurs, plate motions trigger powerful earthquakes. The strongest earthquakes ever recorded have occurred in subduction zones. Rocks in Earth's crust undergo powerful stress caused by tectonic forces, gravity, and the weight of overlying rocks. This slide shows three types of differential stress: tension stress, compression stress, and shear stress. Tension will stretch the rock, compression shortens it, and shear twists or tears it. Rocks respond to this strain by folding or faulting. Folding is bending and faulting is breaking. In other words, stress is a force acting on the rock, and the resulting strain is the deformation in the rock. Whether a rock bends or breaks depends on the rock composition, the amount of pressure, and whether the rock is brittle or ductile. The effects of stress on rocks are clearly visible in the landforms we see today, especially in mountains. Folding occurs when rocks are deformed as a result of compressional stress and shortening. An arc-shaped upward fold is an anticline, in which the rock layers slope downward, away from an imaginary center axis. A trough-shaped downward fold is a syncline, in which the layers slope upward, away from the center axis. In addition to folding, broad warping can cause continental crust to arc upward as if pushed from below. Features formed by warping can be small, fold-like structures called basins and domes, or regional features the size of the Ozark Mountains in Arkansas and Missouri. When rocks are stressed beyond a certain point, the strain creates a break or a fracture. Rocks on either side of the fracture move relative to the other side in a process known as faulting. The fault zones are areas where fractures in the rock demonstrate crustal movement. At the moment of fracture, a sharp release of energy occurs, producing an earthquake. The two sides of a fault move along a fault plane. Three types of faults are shown by direction of movement along the fault as well as the tilt and orientation of the fault plane. A normal fault forms when rocks are pulled apart by tensional stress. When the break occurs, rock on one side moves vertically along an inclined fault plane. Compressional forces associated with a converging motion that forces the rocks to move upward along the fault plane produce a thrust or reverse fault. A strike-slip fault, also called a transform fault, forms when the rocks are torn by lateral shearing stress. The horizontal movement along a strike-slip fault produces movement that is right lateral or left lateral depending on the motion perceived on the side of the fault relative to the other side. And that's it for this video. I'll see you in the next one.